Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is Surface Areas of Revolution. As always, please be an attentive learner while you watch this video. By way of introduction, we're going to be dealing with a different geometrical figure, so we're going to talk a little bit about this. If you take a right circular cone and cut it off part way up, you get something that's called a frustum, and it looks a little bit like a lampshade perhaps. And we're concerned here with the lateral surface area, which means we're painting the outside of the frustum. So that's the lateral surface area, and the formula for that from your geometry, and we could derive it, except I'm just going to give it to you now in this discussion, is going to be pi times r1 plus r2, that is the bottom radius and the radius wherever we cut it off. So it's r1 and r2, the sum of that, times s, and s is the slant height from the bottom to where you cut it off. Now if you dropped this perpendicular here and thought about it for a while, you would realize that s, that distance, is also the square root of r2 minus r1 whole squared plus h squared, where h is the height at which you cut the right circular conical frustum off. And so this is a formula that you have, and we're going to be using this formula in the midst of one of our proofs, because the way we slice things will make it look like a frustum. Now again, this time around we're concerned with the surface area, and you can think about that as how much paint would it take to paint the outside of the container. And as you will see, it's a different concept, and hence a different set of formulas, or formulae as it would be in the Latin. Okay, now the approach is going to seem similar, though. We start with a function, and we're going to rotate the function about the x-axis, getting something like this, and we're going to borrow from our approach that we used for the arc length, where we're going to approximate the function by a series of line segments like that. And here we're doing n equal 4, but we could have done more than that, and we're going to let that go to infinity. But now if you think, what does that mean whenever you revolve things around? You see you get these different colored things that are, so there's blue, orange, green, and I guess I'm going to call that purple. But if you think about those are circular conical frustums, and so we're going to be using our formula for those. So the approximation on each interval gives a distinct portion of the solid, and to make it clear, we've colored them differently, but these are frustums, and we know about the surface area of the frustum. Now the surface area of a frustum is given by, and here instead of calling that S, it's called L, and I didn't bother to change that. But R, in this case, is, as it was before, it's the average of R1 and R2. And L is the length of the side height. Okay, so for the frustum on the interval going from I minus 1 to xi minus 1 to xi, we have R1 is f of x, I, and R2 is f of x I minus 1. Actually, those may be reversed, actually. But anyway, we're going to be talking about the segment. And so we know from the previous section that we use the mean value theorem to find something here. And so this distance along the arc length is approximated by 1 plus f prime at that special point found by the mean value theorem, whole squared, and the square root of that times delta x. And since delta x is very small and f is continuous, there's not much difference between f of x sub I and f of xi minus 1. And so we're going to say that they're both equal to this value in the limit. So the surface area then is going to be 2 pi and we get this expression, which is r1 plus r2 over 2 times that distance, which we know is this. And here we're going to say, since f of xi is almost the same thing as f of xi minus 1, we call them both the same, and we said there's 2 of them divided by 2, so those cancel, and we get this expression. Now the surface area then of the whole thing is approximated by the sum of these, as n goes from 1 to n. And to get the exact surface area, we take the limits as n goes to infinity, and it ends up being this expression. So this is the integral from a to b, 2 pi. This is f of x, and this is the square root of 1 plus, this is y prime of x, whole squared, the square root of all that, dx. And if we did the same thing for x equal h of y on an interval CD about the y-axis, we will get that s is equal to the definite integral from c to d, 2 pi, h of y square root of 1 plus h prime of y whole squared dy. So make sure you understand the concept and where these formulas come from. But realize that the way we often will write them then is that, and we're going to use our notation about arc length before, where we call s, lowercase s, being the arc length, and ds will have 2 manifestations, depending on if we have y equals f of x and x equal h of y. So we get these expressions. You'll remember those from the previous section. So this will be s is equal to the integral, I'm leaving off the limits here, but that is 2 pi y ds when I'm rotating about the x-axis, and s is equal to 2 pi x ds when I rotate about the y-axis, and this is 2 representations of ds. Now there are a couple of things to note about these formulas. First, note that the variable in the integral itself is always the opposite variable from the one we're rotating about. And second, we are allowed to use either ds in either formula. This means that there are, in some ways, 4 formulas here. We will choose the ds based on which is the most convenient for a given problem and given function. And sometimes I will give you directions about which one to use. Let's work a couple of examples now. So I'm asking you to determine the surface area of the solid obtained by rotating y is equal to f of x is the square root of 9 minus x squared from minus 2 to 2. This is a half of a circle of radius 3 centered at the origin about the x-axis. I've sketched a little picture of it here. Here's the piece of the circle that we're looking at. The circle has radius 3. And so, you know, it goes down, but we're only taking this piece and we're taking it around. So that's what we're doing. And we want to find the surface area, so we're using our newfound formulas. You know what to do. Let's see how you did. Okay, now here we have y is equal to f of x, so we're going to use the formula s is equal to the integral. This is 2 pi y, and this is ds. Okay, and that means we're going to be using dy dx. And so dy dx is going to be 1/2 9 minus x squared whole to the, and this is going to be minus 1/2 times minus 2x. And if I simplify that, I get this expression. Now remember, we're going to square dy dx whole squared. So when I square it, I lose the minus sign, and I also lose the square root. And so what I get is, under the square root, is 1 plus x squared over 9 minus x squared. But then I'm going to simplify this by getting a common denominator that is 9 minus x squared. Make sure you follow this calculation, but I'll end up with 9 minus x squared. I take the square root of the top and bottom, I get 3 over, and this is the square root of 9 minus x squared. So this is what we're going to be integrating from, and notice that when I have x here, that means I'm going to have x there, so this is what I'm integrating. But y was this, so you see I'm going to have 2 pi, the integral from minus 2 to 2, and that is going to be this, which is y, times this, which is this factor, and those nicely cancel out. And so I'm really just integrating 6 pi over an interval that is 4 in length. And so if you do that calculation, you get 24 pi. Make sure you understand these calculations. Here's another problem. Determine the surface area of the solid obtained by rotating y equal the cube root of x as y goes from 1 to 2. Now notice that this is a different limit than this one about the y-axis, and I'm going to ask you to do this problem twice. So use both s's, ds's, to compute the surface area, and of course you should get the same answer. I really don't like the picture that I have here, but what we're doing is from 1 to 2 we have the y equals x cubed, and so that's this red curve, and we're taking this around the y-axis. So you know what to do. Let's see how you did. Okay, I ask you to do it both ways. Let's do it this way first. So dy dx in this case is 1/3 x to the minus 2/3, and I square that, and I add it to 1 and take the square root, and I get this. Again, I get a common denominator, and I take the square root of the bottom, and that gives me 3x to the 2/3, and I have this in the numerator. Now we need to deal with our limits though, because we're doing dx, so we have to figure out that x goes from 1 to 8. Make sure you understand why that happens, and then I simplify this by pulling things out. I'm going to do a u substitution to evaluate this integral. I'm going to let u equal what's under the square root. That means that du is going to be 12x to the 1/3. Dx, I make that substitution, and then I also have to change my limits, so I go from, it looks like 10 to 145, and so I do the integration. It's not too hard. I add 1 to the exponent, divide by the new exponent, and plug it in. Now this is the exact answer, so it is pi over 27. That's 145 to the 3/2 minus 10 to the 3/2. Now, you might say that's an ugly answer, but you want to an ugly number, but you want to realize that there are no ugly numbers, just like there are no ugly babies. But that is the exact answer, and that's the answer I would be looking for. Now, if you did it the other way, we'd be talking about saying, oh, x is equal to y cubed. That means dx dy is going to be 3y squared. I'm going to square that, and I get the square root of 1 plus 9y squared. So my formula then is going to be capital S is equal to the integral from 1 to 2. Those are going to be the y's. This is 2 pi. It is now x square root of 9y squared dy. But I'm integrating dy, so I have to put the y cubed in here. Now again, there's really a nice substitution. We let u equal 1 plus 9y to the 4th. And change the limits, and again I get this. Make sure you follow these calculations. Pi over 18, the definite integral from 10 to 145, square root of u du. I plug it in and I get the same answer. And of course you will get the same answer either way. Sometimes it's easier to use one ds than the other, so that depends on what you're being asked to do in the problem and what's the function. I am going to mention in passing that it's possible for us to be revolving the graph of a function about a horizontal or vertical axis that is not one of the, like I could revolve things around x equal -1 or y equal 3 or something like that. And in that case, we're going to talk about r of x be the distance between the graph of f and the axis of revolution. And that would make this r of x and this r of y. And sometimes I ask questions like that on the assessment, so you don't want to blindly use formulas. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.